Hello everyone, welcome to lecture number 4 of the week 6. We will explore in this lecture Darboux's theorem. Darboux's theorem and related some applications of this theorem to solve some problems. So we will cover Darboux's theorem, a statement and mathematical proof of the Darboux's theorem, and then some examples using the Darboux's theorem. So what is the statement of the Darboux's theorem? It says that let f be a derivable function on a closed interval ab, and at the end point f dash a and f dash b are of opposite signs, then there exists at least one point between a and b such that f dash of c is equal to 0. Sometime some of the authors may use instead of 0 some number r or some finite number a and b or c or something like this, right? So let me explain the statement for you. So we have a closed interval a and b, and we have a function fx which is derivable. That means f dash of x exists for closed interval ab, right? And then we have f dash of a and f dash of b are of opposite sign. Then there must exist some c f dash of c such that it is equal to 0. We will going to prove that one in a very simple way. So for our definiteness, sake of definiteness, let's say one of them is less than 0 and other one is greater than 0. So here we have taken f dash of a is less than 0 and f dash of b is greater than 0. Since f dash a is negative, therefore there exists a positive number delta 1 such that fx is less than fa for where? For x belongs to a and a plus delta 1. So since here we have a and here we have b and we have f dash of a is less than 0. So that means for every x in the neighborhood where a and a plus delta, then this neighborhood delta 1, right? What will happen? Each fx is going to be a smaller than fa, right? Similarly, f dash of b is greater than 0. Therefore, b minus of this delta 2, and for this one f of x is greater than f of b. That is the two things which we have already know by the definition of derivable. So since f is derivable in a closed interval, it is continuous in that closed interval. Being continuous in a closed interval, it is bounded and attains its bounds. And let's say since it is bounded in a closed interval a and b, let's say m is the infimum. Infimum means greatest lower bound, right? And there exists c point ab such that f of c is equal to m. F of c is going to be m. M is what? M is the infimum, right? So m is the infimum. It is clear that c cannot coincide with a or b. Otherwise, there would exist points where the values of the function would be less than fc, right? So that's why it is not possible. Thus, c is an interior. Why it's not possible? I think you do understand, right? So fx is less than fa. If fa, I mean at the end point, then fx may not be less than, and then infimum is not possible. So that's why it is not possible to coincide with a or b, right? That's a clear thing. So c is an interior point of closed interval ab. And now we proceed to show that it is this point that where f dash of c is going to be 0. So f dash of c is less than 0, then an interval c and c plus delta 3, where delta 3 is greater than 0, such that for each x belongs to c and c plus delta 3, fx is less than fc, and fc is what? fc is m, right? So we have seen here that okay, so we have c here and then we have a c plus of delta 3 here, right? For this interval we have a here and we have a b here, right? So for this interval we have each fx is less than fc, right, for whole the interval, and fc is what? Fc is the infimum, right, m. So which contradicts the fact that m is the infimum. Now as you can see, fx is less than m, and m cannot be an infimum because it is not a lower bound, it is an upper bound. So greatest lower bound is not possible here, That's why f dash of c is the fact that m is infimum of f, right? So now think about f dash of c is greater than 0, right? So we have here c point here, a here, and b here, right? And we have c. So taking the c as c minus of delta 4. So we have delta 4 here, and we are looking for this interval. Since f dash of c is greater than 0, so each of fx where fx is greater than f of c, and f of c is what? F of c is m, f of c is m, and each of so this one. So that means here we have a c delta 3. So we have shown that it is not possible f dash of c is less than 0 is not possible. Similarly, f dash of c is greater than 0 is not possible because it's contradict the definition of infimum of that point. Hence, the only possibility we have is f dash of c equal to 0, and that's your proof of the Darboux theorem. Now, sometime to prove many theorem, we use a very uniquely defined interior extremum theorem, and it is useful to prove the Darboux theorem, which is in the another form. So it will be recommended that you have to go through the both statement of the Darboux theorem, where we have seen that f dash of c is less than 0, f dash of a is less than 0, or f dash of b is greater than 0. Then there exists a point c where we can find between the a and b, so that f dash of c is going to be equal to 0. You can take this another statement as f dash of b is less than 0 and f dash of a is greater than 0. Then we will have a c point as well where f dash of c is going to be 0. But sometime some of the authors may use instead of 0 r. So we are going to prove that statement where it says that if f dash of a and f dash of b are of opposite sign, then there exists a point c such that f dash of c is any finite number r. That is our statement. So if you have a derivable function in a closed interval, then at end points, if the derivative are of opposite sign, then there exists some of the number c between the a b such that any finite number f dash of c is going to be equal at that point, right? So that is our statement. To prove that statement, let me introduce interior exterior theorem, and without any proof. So I mean, it's quite easy to prove that. That's why it's not given here. So what it says, let f be a function. Let me change the color. So let f be a function from open interval ab to r, be a function differentiable on open interval ab, and if f attains, it's not an open interval, it is a closed interval, right? So I believe that you understand this, right? So attains, if f attains an extremum value at some interior point c of this if this open interval, that is c belongs to ab, then f dash of c is equal to 0. This is also closed interval, right? So then f dash of c is equal to 0. So let me do this. So f is a function from a closed interval ab to r, which is a real valued function, and differentiable. That means at every point f dash of differentiable. That means at every point f dash exists for each point x belongs to closed interval ab. If f attains an extreme value at some interior point c of ab, any extreme value at some interior point of ab, then c belongs to closed interval ab, then f dash of c is going to be 0. but it must be some extreme value at where? Some interior point of that. And in view of that interior exterior theorem of the Darboux theorem, we have another form of Darboux theorem, and it says let f from closed interval ab to r be a differentiable function and r be any number between f dash a and f dash b. So here you have something like this. So you have a and b as a closed interval, and at end points you have sum of let's say here f dash of x. So here we have f dash of a, and let's say b is here, this is f dash of b, right? So between these 2 points, this and this, so between these 2 points, if a number c lying, if a number r, not c, so r is lying between f dash of a to f dash of b, right? Lying between these two numbers, then there exists a number c in AB. So there must be some number c is here, so that f dash of c is going to be equal to r. That is our theorem. And how to prove that? Since r lying between f dash a and f dash of b, define a real valued function g from closed interval ab to r such that g is equal to fx minus rx. That is our construction. So we have already defined a g function from a closed interval ab to r such that gx equal to fx minus r into x. Then g is differentiable. Why? Because fx is differentiable, r is a constant number, and x is a differentiable function, and the difference between the two derivable function is derivable. So that's why g of x is derivable function. So and it value g dash of x is equal to f dash of x minus r. This means g is continuous in a closed interval ab, and we know that every continuous function attains its minimum or maximum in a closed bounded interval. Hence there exists a point c in ab such that gc is minimum of gx from x varies from where? A closed interval ab, in a closed interval ab. So we shall show that c is not equal to a and c is not equal to b, because otherwise the minimum thing is going to be wrong. That's why f dash of a r and f dash of b implies that g dash of a is less than 0 and g dash of b, because f dash of a is what? G dash of a, g dash of a is equal to f dash of a minus of r, right? And we have already known that if r is this number, then g dash of a is going to be g dash of a is less than 0, and which is less than g dash of b, right? So by the definition of the derivative, you know that g dash a is what? G dash a is limit of a functional ratio of the functional value by the argument. So limit x tends to a, fx minus fa divided by x minus a. So taking epsilon as a g dash of a by 2, which is greater than 0, right? And that means g dash of a is less than 0 here, right? This is less than 0. That's why the whole number epsilon is greater than 0. Then there exists some delta such that if delta is less than b minus a, for every x belongs to a and a plus delta, we have f of x minus fa by x minus a minus g dash a is less than epsilon, and that means this is less than equal to 0. By the interior exterior theorem, if using x is greater than it, we get gx minus ga is less than 0, and which implies gx is less than ga. This means that ga is not the minimum value of g, and hence c is not equal to a. Similarly, c is not equal to b. So c cannot be an end point. C cannot be and end points, right, of a closed interval ab, and that means c must lying between closed interval ab. And now interior exterior theorem implies that g dash of c is equal to 0, and that means g dash of c is what? F dash of c minus of r is equal to 0. So f dash of c equal to r. That's your proof, right? So that is the proof of another form of a Darboux theorem. Now, can we use the examples to directly use the Darboux theorem to solve it? So, the first problem you can see here, so that a function fx is given x cube minus of 8x square minus 10, there is some c belongs to open interval 1 2 such that f dash of c is equal to minus 15. Find a value for such a point c. So, I have to find out a value of c between where? Between 1 and 2 such that f dash of c is going to be minus 15. So, firstly, since fx is given x cube minus of 8x square minus 10, I can find out f dash of x, and what will be the value? 3x square minus 16x minus 0, isn't it? So, that means I can find out the end points. F dash of 1 equal to 3 minus of 16 is equal to how much? Minus 13. F dash of 2 is equal to how much? This is 12 minus of 32 is equal to minus 20. So, that means we have minus 20 is less than minus 15 is less than minus 13. This is f dash of b and this is f dash of a, right? So, this means minus 15 lying between f dash a and f dash of b. That means there must exist some number c between the a b such that f dash of c is going to be minus 15. And how I can get that one? So, by the Darboux theorem, we have solved in here that c must belongs to where? 1 and 2, right? So, f dash of c, I have to find out from here f dash of c. F dash of c is equal to f dash of c. So, I can use this theorem here. So, this will be 3c square minus of 16c, and this is how much? Minus 15 is given. Find out c. C is equal to 8 plus minus square root of 19 divided by 3. But we have find out that c must belongs to 1 and 2, and henceforth c must be 8 minus of square root of 19 by 3, and that's your answer. So, now you can imagine that if any function is given, and if it is given that the function is derivable in the closed interval, sum of the closed interval, then we can find out a positive definite number for which any derivative exists and specified. Similarly, take at example 2, where it says that f is defined from 2 to 5 to r is a real value such that f of x is given. So, here we have 2, this is 3, this is 4 and this is 5, and it is given that fx from where to where? From 2 to 3 is equal to 3, and then 3 to 4. So, this whole number is equal to how much? 0, and then 4 to 5. So, here 4 to 5 is given, and this is equal to 7. That is given. So, fx has been the finite value in a piecewise interval, so that there is no function g from 2 to 5 to r differentiable on 2 5 such that g dash is equal to fx for all x belongs to 2 5. So, I have to prove that there does not exist any function g in the such interval 2 to 5 such that g dash of x equal to fx, right. So, on the contrary, let us assume that there exists a function g. So, we had already assumed that g from 2 to 5 r exists and g dash of x equal to fx hold, right. So, now we prove that one by contradiction. So, now g is differentiable on 2 5, and also note that g dash of 2 is equal to how much? G dash of 2 is equal to f of x, and what is the value of f of x? I have written here for you. So, this is 3, right, this is 3. So, g dash of 2 equal to 3, g dash of, so this is 3, and g dash of 5, I have already written here, g dash of 5 is 7. So, this is equal to f of x equal to 7. right? So 4 lies between g dash 2 and, so there is a number 4 lying between these two, right? And hence by Darboux's theorem there must exist C such that g dash of C is equal to f of C is equal to 4. But f never achieves 4, which is a contradiction. Hence there exists no function g from 2 to 5 to R. As you can see here, there is no 4. There is no 4 because all these are the constant number between 2 to 3, 3 to 4 and 4 to 5. So g dash of x never achieve that one, and therefore this is a contradiction by Darboux's theorem, and hence that means g dash never, g as a function from 2 to 5 to R never exists which is differentiable such that g dash of x equal to fx for every x belongs to 2, 5. That's our conclusion. And is there anything which we have to repeat it? Let me repeat by this by the first theorem itself, right? So the first theorem, firstly let me delete this one. So as Darboux's theorem is applicable where you will find out that is there a function which is differentiable in the whole interval, or is it possible or not, and it is also applicable where you can have to show that for a different value there exists a number such that the f dash of C is equal to that number, right? So now we have a Darboux's theorem, and it says that if you have a closed interval a and b, and if you have a function f of x for which f dash of x exists, right? F just exists for every x belongs to where? In a closed interval a b. And if you find out f dash of a and f dash of b of opposite sign, then there exists a number c and such that f dash of c is equal to 0. Moreover, in a general form which has been which we had already seen in another form here, where you will find out that if you take between f dash of a and f dash of b, let's take a number r. R is between f dash of b and f dash of a, then there must exist C belonging to a b such that f dash of C is equal to R, right? And if you are taking R equal to 0, the first statement of the Darboux's theorem is the same one, right? So this statement totally depends, the proof of the statement totally depends on where? On the infimum. That means we have used that any continuous function in a closed interval which is going to be bounded, and if it is a bounded and in a closed interval, then it must have some bounds. It is lower bounds or upper bounds, and so there must exist some infimum or as well as some supremum as well. And once we have to show that this infimum is going to be the same number for which f dash of C is going to be 0. So that was the proof, and as you can see here, m is the infimum here, which is the greatest lower bound, and such that fc is equal to m, right? So that will prove that C is not going to be an end point, it's going to be an interior point, and that's why f dash of C is going to be 0. Similarly, in the next theorem, we had used interior-exterior theorem, and then we have shown that f dash of C is equal to R if you are taking R between f dash of A and f dash of B. And to prove this one, you have to show and you have to prove that there is a function. We had constructed a function gx such that fx minus of rx. So g dash of x become differentiable function, and that's equal to f dash of x minus r, and using the previous one, g dash of x is equal to 0, that will give you f dash of x equal to r, and that's what the proof needed here, right? So that's all, and I think once you go through the both statement, you will find that for any different number between f dash a and f dash of b, there exists some number c belongs to ab such that f dash of c is going to be r. So thank you so much.